Okay, here we are today in section 11.5, continuing our journey on converge or diverge. That is the question, kind of like to be or not to be. But we're going to look at two more tests, and this is the last of the tests for when we're considering positive terms. 11.6, we're going to deal with alternating series where one's positive and one's negative. And what's interesting and fun that you're going to learn is that the alternating harmonic series, remember the harmonic series is 1 over n, the alternating harmonic series is negative 1 to the n plus 1. Basically what's going to happen is it's going to alternate between positive and negative. That one actually converges. So if you tweak it enough to where you're just subtracting a little bit, you get convergence. But that's for the next lesson, 11.6. Right now we're still talking about positively termed series. We're going to look at two tests, the root test and the ratio test. Oh, and I see that I didn't have this covered. Okay, so I'm going to have to write it. Darn. Okay, so here we go. Okay, I just noticed that I did not copy the ratio test down, so I will have to do that for you, but that's okay. Theorem 12 is the ratio test. And what it tells you to do is kind of like when we were looking at geometrics and to figure out what the R was when you looked at a geometric series, or to determine even if it was geometric, you looked at the the next term divided by the previous term to find the ratio. And so if you have a series, A sub n, with positive terms, and we suppose what we do, or we consider, I'm going to say consider, the limit as n goes to infinity of a to the n plus 1 over a to the n. So you look at preceding terms, and you get some value. They're going to call it, it looks like a p. It's actually, in the book, it's a rho. It's a little fancier p. It's Greek. Okay, so then you have some things. Remember with the ratio test, if your rho was between negative 1 and 1, it was convergent. So in this case, it can't be negative because we're only dealing with positive terms. So the series converges if p is less than 1. Okay, but naturally it won't be negative. The series diverges if p is greater than 1 or infinite. And then if you get equal to 1, you have to, you have no conclusion that you can draw. Okay? So, in the end, probably tomorrow before we start, or Wednesday, or the next lesson before I start, or actually at some point in the lesson, I'm going to put all of these on one sheet of paper and kind of give you a strategy for when you might want to use them. But the strategy, this is a useful theorem when you are are looking at series that contain factorials or expressions raised to a power of n. So this is useful when the terms of the series contain factorials of expressions involving n or expressions raised to a power of n. So let's look at a few examples of when this could be fun. Okay, so just investigate convergence or divergence. That's pretty much, I don't know if you've noticed on the homework, that's pretty much what they ask every time, right? Oh, you haven't looked at homework yet? You haven't done any? You're behind. How about you, Brandon? Is it pretty much multiple guess or what?
Yeah, that's all they ask you for.
Is it multiple choice?
Yes.
Oh, wow. You didn't cheat, huh? Cheaters never win, though. Ask the Patriots. All right. Even those, runners that had their glory and then eventually they have to give back their gold medals because they took drugs. Okay, let's look at this one. 2 to the n plus 5 over 3 to the n. All right. Now, you may say to me, Ms. Brooks, well, can I make some sort of argument about maybe comparing this to 2/3 to the n power? The problem with that is 2/3 to the n power does for sure converge, but because you have that plus 5, each of the terms is just a little more, and so, well, then you could make an argument. You could write this as 2/3 to the n plus 5 times 1/3 to the n. And then you could say here, that is 2 geometric convergent series, so it must converge, right? So you could make an argument, a different kind of argument. But let's just use the ratio test because it's kind of fun, all right? Is that okay? Yes, it is, because I'm in charge. All right, so you could make an additional argument. I mean, like already I'm feeling convergence. I guess that's what I'm telling you, because I'm seeing this to be very geometric, or to be written as the sum of 2 geometric series. But I will go ahead and look at a over n plus 1, a to the n plus 1, or a n plus 1 over a to the n. And so what that means is you're going to put n plus 1 in for your exponent. So this is going to be 2 to the n plus 1 plus 5 over 3 to the n plus 1, and that's all over 2 to the n plus 5 over 3 to the n. Okay, and so of course you're going to write this horizontally, or flip it. So this will be 2 to the n plus 1 plus 5 over 3 to the n plus 1 times 3 to the n over 2 to the n plus 5. Okay, and this is kind of something you need to think about. 3 to the n plus 1 can be simplified to be 3 to the n times 3. Does that make sense? So you can think of this as 3 to the n times 3, right? And then you can cancel your 3 to the n's, and you have a 1/3. Okay? So you'll think of this as 1/3 times 2 to the n plus 1 plus 5 over 2 to the n plus 5. Okay? And then let's see if we can clean this up at all. What we could do, and this was a strategy when you're considering limits, one thing that we did, I remember, or one thing when you're looking at something like this, one thing to do is to divide by the highest power in the denominator. Remember, divide everything by. If you divide everything by 2 to the n, that's a legal thing to do, and it's kind of interesting what happens. So if you divide every term by 2 to the n, cool stuff happens. So that's just a little strategy, right? So you'll have 1/3. You'll have 2 to the n plus 1 divided by 2 to the n plus 5 divided by 2 to the n over 2 to the n divided by 2 to the n plus 5 over 2 to the n, right? And this will be 1/3. So what is 2 to the n plus 1 divided by 2 to the n? Yeah, the same logic. This will be 2 to the n times 2, and then the 2 to the n's will cancel, and so you'll just get 2 plus, and I can write this as 5 times 2 to the negative n over 1 plus 5 times 2 to the negative n, right? Now, what is the limit as n goes to infinity of this? We were to consider the limit. What would you get? Yes. As n goes to infinity, these go to 0. And so I do, in fact, get 2/3, which is, implies what? So therefore, by the ratio test, the series converges. Now, it does not converge to 2/3. This is actually one of those ones where you could calculate what it converges to, because you can write it as the combination of two geometrics. But, we don't have to, because the question was only converge or diverge. Okay, let's look at another example. All right, a to the, let's see, n goes from 1 to infinity of 2n factorial over n factorial times n factorial. And these are fun. I mean, it's almost the algebra, like that little bit of algebra that I showed you, you're familiar with, but there may be techniques that you haven't used before. And so factorials are also fun if you have the right attitude. All right, so because cool things happen with factorials. Cool things cancel out. Okay, so I'm going to look at a to the n plus 1 over a to the n. So that's going to be 2 to the n plus 2 times n plus 1 factorial over n plus 1 factorial times n plus 1 factorial, and that's all over 2n factorial over n factorial times n factorial. All right, so let's clean this up. So that I can distribute that 2 out, so that's going to be 2n plus 2 factorial over n plus 1 factorial times n plus 1 factorial, and then times, let's see, I flipped this one, so it's going to be n factorial times n factorial over 2n factorial. Okay? All right, and so this is kind of fun to think about. What you want to look at is n plus 1 factorial. Let me do this in a different color to kind of make a note here. N plus 1 factorial is going to be n plus 1 times n minus 1 times n minus 2, and you continue the pattern. Does that make sense? So because 5 factorial is equal to 5 times 4 times 3 times 2, right? So what happens, and you continue on. So what happens is you write the whatever it is, so the n plus 1, and then you decrease it by 1. Well, that's just going to be n plus 1 minus 1 is just n. And then you start subtracting 1 from that. And so this is really n factorial, right? So n plus 1 factorial can be written as n plus 1 times n factorial. Does that make sense? Okay, and so what's cool about that is that you can cancel, really you can cancel this factorial here and cancel both of those guys. Does that make sense? Okay, so let's see if we can do anything fun with this 2n plus 2 factorial. Is this red too hard to read, Brandon? Are you okay?
It's a little blurry.
All right, so let me try. I'll do a thick blue. So let's play with 2n plus 2 factorial. Okay? Well, what we would do is we would write 2n plus 2, right? And then what would we write? 2n plus 1, and then what? 2n, and then 2n minus 1, yada, 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 right? So all of this part is really what? 2n factorial. Are you okay? Brandon, you all right? It's new. It's not too bad, right? So I can cancel this, and then I have to write this as 2n plus 2 times 2n plus 1, because it took a little longer to get there. Okay, so that's cool. So let me switch back to black. So I can write this as 2n plus 2 times 2n plus 1 over n plus 1 times n plus 1. All right? Now this is super fun, right? Because I could, if I want, FOIL this out, or I could just use my brain and look at the leading term. You don't have to FOIL this out to get the answer, because this is going to have a 4n squared, and this is going to have an n squared. So the limit as n goes to infinity of that will be, does everybody see that it'll be 4? Because it'll be 4n squared over so this is kind of like 4n squared over n squared. I just kind of put it's not exactly, but in the end it doesn't matter. So that simplifies to 4. All right, and so what can we do with that now? So the series does what? Diverges, because p is equal to 4, which is greater than 1. Fun? Okay, so that was one that we dealt with one that was all to the nth powers, which was actually could have been handled a different way. Then we looked at this factorial one, which the factorial ones, really the ratio test is awesome. Otherwise, you can get your comparison test, but that's kind of a scary one. That one was kind of scary. So this next example is going to combine both, and so it should be lots of fun. We're going to look at the series as n goes from 1 to infinity of 4 to the n factorial, over 2 to the n factorial. Now, it's important that you talk to someone about what you're doing in this class so they can be verified at just how totally cool you are. Show someone to that. What'd you do today? This is what I did today. They'd be like, oh my gosh, you're so smart. And you'd be like, I know. And then they'd say, why are you doing that? And you would say, because I can't. Okay, all right. So we're going to look at a to the n plus 1 over a to the n. So this is 4 to the n plus 1 times n plus 1 factorial times n plus 1 factorial over, 2 times n plus 1 factorial, and that's all over 4 to the n times n factorial over 2 to the n factorial. All right, so I'm going to flip this and then do some thinking. 4 to the n plus 1. This is n plus 1 factorial, n plus 1 factorial, over, I'm going to distribute that out, 2 to the n plus 2 factorial times the flip, which is 2n, should be saying 2n factorial. Now here's my 4 to the n, and then an n factorial and an n factorial. Okay, Brandon, what can cancel? Don't put your hands on your face. Scott's making me eat this extra cookie.
The n factorials with the factorial
Right, because
thingy
this,
on the n plus 1.
yeah, because after a while, the first, it would be n plus 1 and then times n minus 1, so the pattern. So I can cancel, I'll change colors. I can cancel this guy with this guy, and then this guy with this guy. Okay, anything else?
The 2 to the n factorial with the factorial on the 2 to the n plus 2.
Right, I have to think of this as 2 to the n plus 2 times 2 to the n plus 1 times 2 to the n factorial, right? Because it'd be 2 to the n, yeah. So that cancels with that, and I end up with that stuff. All right, there's something else. I have to go to the red because it's the only color I have left.
4 to the n.
Good. This you can think of as 4 to the n times 4, right? So you can cancel the 4 to the n's. So we end up with 4 times n plus 1 times n plus 1 over 2n plus 2 times 2n plus 1, which is equal to, now let's consider the limit. So let me put limit on there. And let's think about what happens. Anybody? It's going to be 4n squared over 4n squared, right? So that limit's going to be equal to 1. And what did it tell us?
Non-conclusive or something like that. Inconclusive.
Is it inconclusive? If it's equal to 1, you're out of luck? Yes.
Yep.
Crud. Okay, so we have to think about it some more. All right, now, okay. What they tell you to recognize let me see. I wonder if you could, I'm trying to see if you could see it sooner. So they're saying when we notice that a to the n plus 1 over a to the n, okay. Okay, let's just play for a second. If I write this as 4 times n plus 1 times n plus 1 over, if I factor the 2 out of this, I'll get an n plus 1 and then a 2n plus 1. And so this is 4n plus 4 over 4n plus 2. Do you agree with that? Now, while the limit does go to 1, what you do notice is that this term, the next term, this is like your a to the n plus 1, is always just a little bit greater than a to the n, right? Which means that it does not go to 0.
Your conference is scheduled to end in 2
It doesn't
minutes.
pass the nth term test. So since a to the n plus 1 is always larger than a sub n, the series does not pass the nth term test, which implies that it diverges. But I'm not really sure that you would have been able to look, if you just looked at the nth term test, if you just considered this limit right here from the beginning, it would have been really, we don't really have a strategy to consider that limit. You kind of had to do some work before you could make that argument. Just looking at this limit, seeing that it doesn't go to 0 is kind of tricky.
So before the end, it's going to go a lot bigger than n factorial.
Yeah. It does sort of seem like this is going to beat it out over 2n factorial. You could probably look at a few terms and see that they're always getting bigger too. Okay, so that one was inconclusive. Inconclusive is never very fun. I'll try to give you all ones that are conclusive. Okay, another test is called the root test. And it's good if you have an extremely, it's good when you have a complicated.
Your conference is now over. Goodbye.
It's good when you have a complicated series. They actually say in the book, it says, the convergence tests we have so far for the series A sub n work best when the formula for A sub n is relatively simple. And I'm not sure that these have been relatively simple, but they look at one that's an example of what they would consider more complicated one. We'll just look at their example from the book. This is example 2 from text. They are looking at, they let A sub n equal n over 2 to the n, and then 1 over 2 to the n. It's n over 2 to the n when n is odd. It's 1 over 2 to the n when n is even. And they want to know, does the series A sub n converge? So that's certainly more complicated. Now, one thing that you can always do is what? What's the first thing? Whenever, if you don't know how to do, if you don't know what to do, what should you do first? Well, the nth term test, but you can probably argue pretty quickly that it's going to pass the nth term test. Right? Can you? Yeah. And so that's for sure. The nth term test is a good one. I always, if I get really weirded out, I might write out a few terms to kind of see where I'm at. So, okay, when n is 1, that's odd. So it's going to be 1 over 2. And then it's going to be 1 over 2 squared, which is 4, plus, this will be 3 over 2 cubed, which is 8, plus 1 over 2 to the 4th, which is 16, plus, now I'm going to do 5. 5 over 2 to the 5th, which is 32, right? And so it's not geometric because I don't have a common ratio. The nth term does go to 0, so it passes the nth term test. The integral test, you know, x over 2 to the x, how are you going to integrate that? 1 over, you know, for even and it feels a little painful to integrate, right? X over, let's see. The integral test seems painful.
Miss Rose,
Yeah?
it's not geometric.
It's what?
Oh, never mind.
Are you good? Okay, so the integral test seems
Didn't see
painful.
your theory.
If you look at the ratio test, let's see, what would we have? Well, let's see. A to the n plus 1 over a to the n is going to be equal. Well, again, it depends whether n is even or odd, right? If n is odd, then that makes a to the n plus 1 even, right? So it'll be 1 over 2 to the n over n over 2 to the n. So, 2 to the n plus 1. So that would be equal to, how does that clean up? Sorry. Let me read it. Sorry. How do I do that? What do I do? I'm on the record. I'm on video, muting my phone. Sorry. Okay. This cleans up 2 to the n times 2. And then this is 2 to the n, so those are going to cancel, and then you're going to have n, so it's 1 over 2n if n is odd, right? And then if n is even, then that makes then a to the n plus 1 odd, so that's n plus 1 over 2 to the n plus 1 over 1 over 2 to the n. When you flip that one, you're going to get n plus 1 over 2 when n is even. Okay, and so it's either a small, and so the ratio as n goes to infinity either is very small, right, or very large. So it doesn't, it's no good. You don't get it. So not helpful. So if you look at the limit as n goes to infinity, it's inconclusive. Because it depends whether you're even or odd. So what we're going to look at then is what's called the root test. Okay, look below. So the root test says let the series a sub n, let it be a series where a sub n, again, positive terms, for n sufficiently large, so, eventually, if you're able to show that the nth root of a to the n is equal to some row or some p number, then it will converge when p is less than 1, it diverges if p is greater than 1 or is infinite, and is inconclusive if p is equal to 1. Okay? So let's see how that would help us in this problem. Okay. We still have a sub n is equal to this n over 2 to the n versus 1 over 2 to the n if n is odd and then if n is even, right? Okay. And then the limit, oh no, we don't have to do the limit. What we want to do is look at the nth root of a to the n. Okay? So the nth root of a to the n, well then we would look at the nth root of n over 2 to the n when n is odd, or the nth root of 1 over 2 to the n when n is even. Okay. So what's the nth root of n? Well, not necessarily. It feels like it would be 1, doesn't it? But the fifth root of 5 isn't.
Right.
It is just what it is. Okay? But the nth root of 2 to the n is what? So we know, what about this one? What about the nth root of 1 over 2 to the n? This one is going to be, okay, so this is going to be the nth root of n over 2, or the nth root of 1, or this is just going to be 1 over 2. This one's 1/2. Okay? Okay, now the nth root of n, we actually learned this. Or actually, so you were right. The limit as n goes to infinity of the nth root of n is, in fact, did you say 1? Yeah, okay, so you remember that. That's good.
No, I didn't. I got lucky.
Okay, that's really good, because it doesn't necessarily feel, like the square root of 2 is 1.41. I forgot that, but we did, I don't know if you remember that theorem. We looked at those theorems of things we should remember in section 11.1. I think it was like theorems we should remember, and that the nth root, as n goes to infinity, the nth root of n, it's like saying n to the 0, which is 1. But, so, we know that this goes to 1, which means that this thing is sandwiched in between, it's going to 1 as n goes to infinity, so you've got it sandwiched in between 1/2 and 1/2, kind of almost 1/2, you know what I mean? And so you can write 1/2 is less than or equal to the nth root of a sub n, which is less than or equal to the nth root of 2, but this goes to 1/2, so you're going to be able to argue that that goes to 1/2. Goes to 1/2, which by the root test does what? Yeah. Root test the series converges. Whew. Okay. So let's look at, I just stole these examples from the book. Let's look at some examples, some additional examples. That one was kind of tricky. Okay. N squared over 2 to the n. So say it was on the test and I had to look at that one and I don't know what test to use. I'm probably feeling pretty good. I mean, it clearly passes the nth term test. I don't feel like touching an integral with that, because I don't like integrating that much. I don't feel very good about, I guess I could do the ratio test, but I'm not sure how that would help. But the nth term test kind of feels good because I've got that 2 to the n. So let's see what happens. I mean, the root test feels pretty good because I've got that 2 to the n. So if I do the nth root of n squared over 2 to the n, I get the nth root of n squared and the nth root of 2 to the n, which of course is just 2. Now, the nth root of n quantity squared is equivalent to the nth root of n squared. That's from algebra, right? And so this goes to 1 by that theorem as n goes to infinity, and so 1 squared would also go to 1. And so you get 1/2, which is less than 1, and so you can say that it converges. So that's a pretty quick one to say that it converges. Now, how about the next one? What if we were to reciprocate it and you get 2 to the n over n squared? Well, it feels like you probably get 2, right? Because you would just reciprocate this, which is greater than 1, which would make it diverge. But, I mean, I think I would argue, I guess it's not a very clean argument, but if I had a race, I would put my money on 2 to the n. So I would say that this, I would have argued that this diverged by the nth term test. But the root test is nice on that one as well. Does that make sense? Okay, how about this one? If we take the nth term, the nth root of this to the n, it's just going to be 1 over 1 plus n. And as n goes to infinity, well, I don't have it, C. Over 1 plus n to the n. All right, well, the nth root of 1 over 1 plus n to the n is going to be equal to the nth 1 over 1 plus n, right? Which as n goes to infinity, what is that? Where does that guy go? This little arrow means look at the limit as n goes to infinity. Where am I going?
The plus is going out there, so it's 0.
It's going to 0, yeah. Right, 1 over n goes to 0, 1. Okay, so if it goes to 0, that's less than 1, which means that this series does what? Converges. Okay, so pretty fun, right? Okay. Should we try some more problems? Y'all want some more examples, or are you heading a couple more? Sure, Miss Brooks, let's do some more. Okay. You seem a little excited. You seem better than you were on Monday, Brandon. I mean, you look a little more awake. The Easter Bunny was good to you. Here's one. Let's do one with E. I love E. So this is from, or form, F-R-O-M, from the online text. Or online, no, this is from the textbook exercise. I was thinking of just like, instead of looking at magazines when I'm bored, I was just going to start working like every single problem in the calculus book. What do you think? Hey, don't give me that face. I thought that would be a good idea.
Is he bored?
Because now I don't know. Or I could just stare at my toenails. The series n goes from 1 to infinity of n factorial e to the negative n. I ought to do that. I ought to just put my calculus book on the coffee table, and then whenever I'm just like, what am I going to do? I could pick a problem. Okay. What test do you want to do? The reason I don't want to do the root test is because I don't really know what to do with a factorial in a root. That's creeping me out. So I would prefer to do the ratio test. But you can do the root test if you want. Yeah. Okay. So I'm going to do the ratio test because I remember that with the ratio test I had some cool things canceling. So I'm going to look at the limit as n goes to infinity of a to the n plus 1 over a sub n plus 1 over a sub n. Okay. So that'll be n plus 1 factorial over e to the negative n plus 1 over n factorial e to the negative n. All right? Okay. Why is this thing is like got a brain of its own? Okay. So you could write this as n plus 1 times n factorial. Does that make sense? And then actually I can flip these guys because they're negative. And that means they want to move to the other spot. So this is e to the n. And then I still have this n factorial. And this is e to the n plus 1. Are you okay? Everybody okay with that? Yeah. All right, so this cancels with this. And then I'm going to have, what am I going to have? Yes, I will have an e to the n and an e to the n times an e, right? So the e to the n cancels, and I'll have an e left, e to the 1, kind of. So I have n plus 1 divided by e. Okay? So what is that limit? Where does that go? That goes to infinity. And so we now know that this series diverges. Okay? Interesting. Because, I mean, on the nth term test, you probably, because you think of this like this, right? You know that these terms, you can probably argue to yourself they go to 0. Because, well, I don't know. It depends what n is. If n is like 5,000, but then you'd have e to the 5,000, which is like 2.7. Then, I don't know. I wonder if it would have failed the nth term test. I don't know. It was easier to look at it with the ratio test. Okay, let's do another one. How about we did an e, so not to be left out. ln n to the n over n to the n. All right, let's look at this one kind of begs you to use which test? What am I begging for? The root test. Does it feel like the root test? Because we get to look at the nth root, and right. Okay, so we do the nth root of a sub n. It's going to be the nth root of ln n to the n over n to the n. I wish there were more n's in this problem. All right, so this is ln n over n, right? And so what is the limit as n goes to infinity of ln n over n? Yeah, remember ln n is like the world's slowest function. And we proved that n to any power grew faster or something, or we talked about it at least. So that's going to go to 0. And so what does this series do? What converges? Good. Okay. Here's one. For some reason I'm just going to throw some out, and so you may not have to use one of the new tests that we just looked at today. What would you say about this one? 1 over n minus 1 over n squared. You want to do that one? If I was going to do that one, I think I would at least want to get a common denominator before I started doing that, you know? So I would at least want to write this as the series n goes from 1 to infinity of n squared minus 1. No, just n minus 1, right? Because this one will have to be multiplied by n over n. So n minus 1 over n squared, right? Okay, and so you want to do the a to the n plus 1, a sub n plus 1 over a sub n. Okay, and so then that is n plus 1 minus 1 over n plus 1 squared over n minus 1 over n squared. So this is n over n plus 1 squared times n squared over n minus 1. And what do we get? Where's that go? It behaves a lot like n cubed over n cubed, right? So that limit, it goes to 1. Do you see that?
I was writing it down.
Which is, what is that? That's a bummer, right? The bummer, that if it's equal to 1, then that's a bummer. Okay, so try something else. So it's inconclusive. All right. What about we learned? What was the one we learned last time? Did we learn anything? Which ones did we learn in the other section? Like in 11.4, we learned about the limit comparison test, right? Let's see if that one would be any fun. If we could compare it, you know, like we compare it to the series, right? We come up with a series and we compare it to it. Okay, so let's look. Does this, I mean, would you like to compare this to anyone? I mean, does he look like anyone you'd like to compare him to? Yeah, say it again. Yeah, it kind of, like if you just kind of forget about the minus 1, and it kind of looks like 1 over n. So we could try the limit comparison test using 1 over n, which is our b sub n, right? So we look at a sub n over b sub n. We look at the limit as n goes to infinity. All right, well, a sub n is this n minus 1 over n squared over 1 over n. So this will be the limit as n goes to infinity of n minus 1 over n squared times n over 1, which is equal to the limit as n goes to infinity of n minus 1 over n, which is 1. Okay? Well, what did the limit comparison test tell us if we got it equal to 1? If it's equal to some constant, it just has to be positive, which it is, then they either both converge or both diverge. So what can we say? Right. So by part 1 of the limit comparison test, LCT, it diverges. Because 1 over n diverges. So what you do is you kind of, you know, you try some tests and then you have to try others to try and get there. And then if you don't know, you just pick a letter and move on. It's almost like I need to make this test one that I grade because I'm afraid y'all are just going to pick letters. And how am I going to do that? How am I going to make sure you're really doing this? Could you get a 50? I could ask you what the probability, if you guessed on every one of them and there were only 2 choices, what are the chances that you pass? Okay.
It's actually 50% of, isn't it?
No, it's not 50%. It's 50% on any one.
On any one.
But yeah, it's actually 0.5 to the however many problems you have. So if we had 20 problems, it would be 0.5 to the, I guess that's the chances of making 100. So then you'd have to set your probability of whatever you want for your pass. So, yeah. We don't ever do a question that hard in statistics. Okay, so I think that's probably enough. You can play with these and see how much fun you can have. Again, remember to practice. Practice makes perfect. All right, so I'll talk to you later.